is the new black. Vantablack absorbs 99.965% of visible light, making it the world's new darkest material. At this degree of darkness, it is impossible to decipher when the material is folded or crumpled. This is Vantablack on a crumpled piece of aluminum foil. Take note that you cannot see any of the folds or wrinkles. Stemming from the research and advancements made from Belgian artist Frederik de Wilde along with his collaborations with NASA, Vantablack is a current project being produced by Surrey Nanosystems out of the UK. But what is Vantablack exactly? Vantablack was named for its unique microstructure. VANTA stands for Vertically Aligned Carbon Nanotube Array. In order to understand how this microstructure makes it possible for Vantablack to work, we must first take a look at what carbon nanotubes, or CNTs, are. Carbon in the nanophase can exist in some allotropic forms like graphite, diamond, and Buckminster fullerene, also known as fullerene. Fullerene consists of a family of spheroidal or cylindrical molecules with all the carbon atoms sp2 hybridized. A carbon nanotube is a tubular form of carbon with a diameter as small as 1 nanometer. A carbon nanotube is configurationally equivalent to a two-dimensional graphene sheet rolled into a tube, whereas graphene is a single atom thick sheet of graphite. CNTs can be either single-walled or multi-walled, with multi-walled CNTs ranging anywhere from 2 to 20 layers thick. Vantablack is made up of vertically aligned multi-walled CNTs. CNTs are the strongest, most flexible, and stiffest material in terms of tensile strength and elastic modulus, respectively. CNTs have a very high current carrying capacity and have highly variant conductivity depending on the plane of current flow. Several production methods have been developed for the synthesis and growth of CNTs, including arc discharge, laser evaporation, and the method most currently utilized, chemical vapor deposition, or CVD method. CVD, in short, produces CNTs from a carbon-containing source, usually in a gaseous form, decomposing at elevated temperatures and passing over a transition metal catalyst. Synthesis through CVD has many advantages. The material has less impurities that occur in the form of nanoparticles of graphite or of metal. Along with this, lower temperatures are required for CVD synthesis than any other methods. Lower temperatures make the process cheaper and more conceivable in labs. Also, the metal catalyst can be held on a substrate or surface where reaction occurs, enabling growth of aligned nanotubes in a desired direction. It's been observed that there is a correlation between the growth and nucleation of CNTs and the electron structure of the metal used as a catalyst. The metals most currently used for CNT synthesis are nickel, copper, and iron. These metals have few d orbital vacancies. The carbon is initially deposited and thus activates the catalyst, forming metal carbides on its surface. A carbide is a compound composed of carbon and a less electronegative element. The metal carbides segregate part of the dissolved carbon, causing them to form the first graphene layers. This is the nucleation part of the process that marks the beginning of the carbon nanostructure formation. This step then allows more particles from the carbon source to be decomposed due to carbon concentration gradient in the catalyst. The released carbon atoms assemble into graphene layers and form the body of the carbon nanostructure. This is the growth portion of the process. Although it has yet to be released as to just how Vantablack is produced, it's likely that the CVD method is utilized, using a catalyst particle that is a few tens of nanometers in size to create multi-walled nanotube growth in the desired direction. It's likely that this process takes place within the current known temperature for CVD, which ranges from 550 to 1,000 degrees Celsius. The current primary applications of Vantablack's ability to trap light are in optics. A key aspect of any good telescope is to minimize any stray light in the light path and the focal plane. Stray light from sources besides a desired faint image will be focused to the same place as the faint object, distorting the image. An extremely dark interior is crucial to absorb the remaining photons. Vantablack makes a great interior because its CNT makeup will absorb more stray light than any other material known to man. How exactly does Vantablack absorb light? Vertically aligned CNTs make up 3% of the total volume of a carbon nanotube forest, leaving the other 97% to be just air. The tubes are arranged perpendicular to the substrate, and the light enters the forest and interacts with the nanotubes. Since the tilt angle is small, little light is reflected back out. Instead, it travels around through the forest and is simultaneously absorbed by the nanotubes. This continues until the majority of the light is absorbed. The sparseness and alignment of the nanotubes in a carbon nanotube forest are the key drivers in the low level of reflectiveness of these types of materials, especially Vantablack. Vantablack could have applications in a number of telescopes, but would be most practical in telescopes that require precise imaging. Other alternatives to Vantablack, such as a chalkboard paint, are effective with visible light, but fall short when it comes to other wavelengths. Vantablack is effective across a huge spectrum, from ultraviolet to visible light to infrared to microwaves. The Integral is a telescope aimed at determining how elements are formed when a star dies. The International Gamma Ray Astrophysics Laboratory was the first space observatory that could simultaneously observe objects in gamma rays, X-rays, and visible light. We feel that Vantablack would apply well to the Integral due to its ability to absorb light from a wide array of wavelengths, but its space applications will likely span much farther than a single telescope. After exposing the coating to space qualification testing, the results showed no changes in hemispherical reflectance value. The consistency and durability of Vantablack, due to the unique properties of CNTs, is a major indication that a material can successfully be utilized in future space observation applications. Although some were hopeful, Vantablack will unfortunately not be made into clothing or used for everyday purposes. No little nano black dress, or at least not yet. This is due to certain costs and safety issues that may arise. Carbon nanotubes can be potentially harmful if inhaled. However, since the average citizen won't come into contact with the material, there is little need to worry about any safety threats. Also, although the price hasn't been released, the higher absorbance capabilities results in reduced use of the material, thus offsetting the higher per unit area cost. This groundbreaking material has the potential to improve a lot of research being done by other fields, especially that of space companies in their pursuit of the better monitoring of space around us. As material scientists continue to make advances in the study and synthesis of carbon nanotubes, Vantablack and other future nanotube materials may have extraordinary impacts in space exploration, defense applications, and potentially in our day-to-day lives.